Hi there, it's Paul with a script designed to show you that, at least in examples, the rules for forming derivatives of sums, products, compositions, etc. of functions work just the same way in multivariable calculus that they did in single variable calculus. If you haven't already done so, install the numderiv package, then comment out the line so you don't repeat the installation. In any event, you need to call the library function so you'll have access to the gradient and Jacobian functions. What I mean when I say that a scalar valued function of a vector is differentiable is that if I calculate the directional derivative along a direction vector v, the result is a linear function of the direction vector. In other words, I can calculate it knowing the directional derivative for the standard basis vectors. Those directional derivatives are called the partial derivatives. And your second proof for this week is to prove that as long as the partial derivatives are continuous functions, this will always be the case. So if I write down a formula using any reasonable function, basically something where I don't divide by 0, I'm going to create a differentiable function. I have to write this as a function of the two components of a vector. To read this as a function of x and y, you'd read it as f1 produces the function sine x times y squared divided by 1 plus x squared plus y squared. We have to test for differentiability at a specific point. I've picked one arbitrarily, and I've picked an arbitrary directional vector. I calculate the directional derivative as a derivative of a function of a single variable t, basically saying I'm going to move a short distance t along the vector vv, the directional vector, subtract off the value at v0, take the derivative of that function with respect to t, and evaluate at t equals 0. That's the directional derivative. Alternatively, and much more simply, I can just take the gradient of the function f1 and calculate its dot product with vv, or equivalently, matrix multiply the Jacobian matrix by the vector vz, and I get the same answer. Now let's try this with a non-differentiable function. If you want to cook up a function that's non-differentiable at the origin, here's how to do it. In the denominator, use x squared plus y squared, v1 squared plus v2 squared. In the numerator, pick something that is cubic in the two components. Since the numerator has 3 powers of the components, the denominator 2, this function will go to 0 as the two components of the vector approach 0. It'll be a continuous function, but because you've got that 0 in the denominator, you have to tell R explicitly that if the vector where you are evaluating the function is the 0 vector, the value is supposed to be 0. That's the purpose of that if-else. We're testing at the origin. Pick any old vector for the directional derivative. If you want to try this on your own, you can try with a vector that's directed along one of the coordinate axes. In that case, you'll actually get the correct answer. Here's the correct calculation of the directional derivative. It gives 1.87. Here is what you get calculating from the partial derivatives. This is assuming that the change in the function is well approximated by a linear function of the directional derivative. It's not, you get quite a different answer. And in fact, in this case, the partial derivatives will give the wrong answer for any direction vector that's not along one of the coordinate axes. So let's generate a random one, something with two components that are in between 1 and 3. Evaluate the directional derivative, get 0.42. Try to compute the same result from the partial derivatives, get something about 10 times larger. Now let's look at derivative rules. Here is a function from R2 to R2. If you want to read it as a function of x and y, you can say the first component is going to be x squared plus cosine y, and the second one is going to be e to the x times y. Here's another function. This time it's made up using square root, sines, cubes, etc. The exact choice of the function doesn't really matter, since these functions can be written using ordinary formulas and don't involve division by zero. They're going to be nice differentiable functions. Here is their sum. Here is the product of the function f1 that I introduced at the start of this script times g1. Here is just the first component of the function g1, and here is the product of f1 with that first component of g1. Here's the composition of the two functions. Here's the dot product of the two functions. Since I haven't loaded a library with the dot product function, I'll just compute dot products by asking R to multiply the two vectors together and sum up the products. Now we can check all the differentiation rules. We have to pick a place for evaluation, calculate the Jacobian of the sum of the two functions, calculate the sum of the Jacobians. It comes out the same. Check the chain rule. Pick an evaluation point, calculate the Jacobian of the composition of the two functions, g1 composed with g2, and then compute what the chain rule says should be equal. This one you have to be a little bit careful with, because you take the Jacobian of g1 and you evaluate it at g2 of the vector v0. Then you matrix multiply that by the Jacobian of g2 evaluated at v0, and it comes out the same. Let's try the product rule. First, let's try the product rule in the case where you are going to be proving it, where both functions are scalar valued. Pick an evaluation point. The function that we got by multiplying two scalar functions together was called gprod1, and there is its gradient, or if you want to read it as a row, its Jacobian matrix. The product rule says f1 times the derivative of g1.1 plus the derivative of f1 times g1.1. Basically the same rule as in single variable calculus, and it gives us the same answer. If you're trying to check this out for scalar valued functions times vector valued functions, you discover to your annoyance that we have no notation that represents the derivative function, so we have to evaluate on a specific increment vector. That means I need not only my v0, but a vector vv on which I'm going to evaluate the result. So I can take the Jacobian of the product, I evaluate it on vv, and get a two-component vector. I can do the same thing as the sum of two terms using the product rule. In the first term in the product, I differentiate the second function, g1. In the second term of the product, I differentiate the first function, f1. And in either case, I evaluate the thing that's not just a number on the vector vv, and I get the same answer. Finally, the dot product rule. This is proved in the book, and it's a rather tedious proof. Again, we need an increment vector, so I can take the dot product of the two functions. This turns out to be quite an important operation in physics, evaluated on vv. Alternatively, I can calculate the dot product of the Jacobian of the first one, evaluated on vv, with the second one, and add on the dot product of the first one with the evaluated Jacobian of the second one. I get the same answer, and we are done.